All right, we're going to finish up section 8 and try to finish up the chapter by doing the derivatives of inverse functions, inverse trig functions. Review. The derivative of the natural log of absolute value of x is 1 over x. And the derivative of ln b of x, remember what b is, as long as it's positive, is also 1 over x. The b's cancel because it's a constant. That's what we did up to section 7, up to half chapter 8, section 8. Now we're looking at exponentials and logarithmic, the general formulas for derivatives of those two functions. And the review, we also talked about the derivative of an e function, the exponential function. E to the power u is eu du. That's a review from what we've had in the past. To begin with, let's look at y equals a to the power u. Well, let's start with a more specific function first, a to the power x, where a is any number that cannot be 0 or 1 or negative. A's got to be positive, cannot be 0 or 1. And the graph of an exponential function looks like this. It's an increasing function that never crosses the x-axis. Since we've talked about the derivative of the e function, we can rewrite this equation. We can rewrite a to the power x as e to the power ln a to the x. Let me see. Yes. Because remember the properties of logarithms, one of them says if we have the same base, the base and the base of the logarithmic function, then it equals what the operation is. That's from algebra. Since the bases are the same, they cancel. So it's just x. So E, also review, ln x is the same thing as log base E of x. Now, another rule of algebra, reviewing the exponential rules, that if we have an operation raised to a power, that exponent goes out in front. You cannot have exponents in logarithmic functions. You know, these are just all algebraic functions, properties. If you have an exponent, it goes out in front. And that's what we have here. In this equation, this exponent goes out in front of that. So we have x ln a. So all of this, we can rewrite a to the power x as e to the power x ln a. So if we take the derivative of both sides, because we're finding the derivative of a to the power x. Since we have an e function, the derivative of e to the power u is write down what you have. times the derivative of the exponent. The derivative of x ln a is simply ln a. So x ln a. Well, the derivative with respect to x that goes away, so it's ln a. So what we're left with is ln a e to the power x ln a. Well, we know what e to the power x ln a is. We did that conversion up here. That equals that. So what we have here is ln a times a to the power x, or you can write a to the power x ln a. That's the derivative of a to the power x. So there's our formula for derivative of a to the power x. Because we can rewrite a to the power x, you came here late. We can, this is the same thing because of the rules of exponents. And all we do is just transpose them. We can also extend this to the e function, where the derivative e to the power x is e to the power x ln e, which is e to the power x. This equation here is only good for x. What if we had an equation where u is a function of x? Okay, it's the same thing. It's a to the power u times ln a times the derivative of the exponent, du dx. This is a general formula. So in this section, we're taking the derivatives of a to the power u, and we end up with this. Later on, we're going to do the ln function. All right, let's look at some examples. So let me first rewrite that formula up on top. The derivative with respect to x of a to the power u is a to the power u ln a du dx. That's a formula we'll be dealing with. So here's the first one. A, find the derivative of 3 to the power x using that formula. Because if you look at our formula here, we have to define what is a, what is u, and what is du dx. those are the three things that we have to find. Once we find those, just plug them in there. So in our example, what is A? 3. What is U? X. What is du dx? What's the derivative of U? No, what's the derivative of X? 1. Because this is, here's U. Take the derivative of U with respect to X. The derivative of X is 1. So now all we do is just plug them in there. So we have A, which is 3 to the power X, ln 3 du dx is 1. So our answer is 3x ln 3. Find the derivative of 3 to the power negative x. Again, to use this formula, what is A? 3. U is negative x, negative 1. So we have 3 to the power negative x ln 3 times negative 1. So the answer is negative 3 to the power negative x ln 3. And if you want to go further than this, it would be negative ln 3 over 3 to the power x, because the negative exponent. Find the derivative of this function. 3 sine x. Again, well, we have to find A, U, and the derivative of U. A is 3. U is the exponent, which is sine x. The derivative of sine is cosine. Let's just plug them in there. So we have A to the power U, which is 3 to the power sine x times ln A times the derivative, which is cosine. Three sine x cosine x ln 3. It's just really just a matter of plug and play. Matter of plug and play. Any questions so far? At least because, well, is this ln 3 cosine x? Is it all one equation, or is it two separate equations? It's just for ease of reading. This is cosine of x times ln 3. Is it so you don't get, this is not 3 cosine x. This is ln 3 times cosine of x. Or you could put those in parentheses. It's just so you don't get those confused and overlapping themselves. That's a very good question. Is why do we do that? It's just ease of reading. It all started back when I was, if you had x plus y times 2. A lot of people got that mixed up. They think that that 2 belongs to the y. And so that's why whenever I write square roots, I put a little hat there that tells me this is the end of the square root. So that's why I want to separate all my numbers to make sure I don't get them confused. All right, so far, all of the functions we've used were ln or natural logs. What if we had any other base than e? Because remember, ln is log base e of x. And if you think about it, all of our formulas are dealing with ln. So if we have log base a of x, since we have where a is not e, there's any other value other than that. So what do? We have to put it into terms of ln. How do we do that? If we have a, which is not equal to e, which is that. We have to make it into ln by using the change of base formula. So we use a change of base formula to put it into ln function. So we take the derivative of a function log base a of x. So the first thing we have to do is we have to rewrite our log function as ln. So we use the change of base formula. Now it makes it much easier. Because remember, we're only taking a derivative with respect to x. So that means this is a constant. ln a is a number, it's a constant. So I could bring that out in front. So we have 1 over ln a. What's the derivative of ln x? One over x. So it equals 1 over x ln a. That is the derivative of log base A of x. That's the formula we have to use from here on out for that. Again, this is when we deal with x. What if x is an equation? We can rewrite this also as log base A of u, where u is a function of x. That equals 1 over u ln A times the derivative of your function. Let's look for an example here. So far, so good? I'll just make up an example here. Y is equal to log base 3 of 2x squared plus x. Find the derivative. Remember, the formula, we'll have to use this formula here. 1 over u ln A du dx. Well, it's not A, it's ln A ln u. So what's our, according to this format, what is our u? What is our u? Remember, yeah, u is that. So this it should be ln u. Yeah, this whole thing is my u. 2x squared plus x. Then I have to find the du dx, which is u prime, which makes it 4x plus 1. So now just plug it in there. On the top is my derivative, which is 4x plus 1. That's my derivative of u. And on the bottom is 2x squared plus x times ln of 2x squared plus x. And there's your derivative. Oops, hold it. I'm sorry. Oops, oh, my bad. Hold on. What is A? A is the base, 3. So that should be 3. This is the base. This is the operation. And so there we have it. So my final answer is 4x plus 1, 2x squared plus x times ln 3. Plug and play. Now, the beauty of this whole process we're doing here with LNs is, what if I gave you this equation? Well, we can use logarithms to simplify the derivative of a complex function. By complex, I simply mean that it has a lot of parts to it. Example 6. Find dy dx of this function. Y is equal to, let me put it down here, of y is equal to x squared plus 1, x plus 3 to the power 1/2 over x minus 1. Originally, if you were to have this as a homework or a test question, you wouldn't have this power 1/2 here. What you would have would be square root of x plus 3. So from there, you would have to take it and make it into 1/2. Okay, so how would you solve this? What method would you use to solve this? We have a product here, we have a quotient. Would you use the product and quotient rule? That would be very, very time consuming. With the properties of logarithms, if you have a product, you can separate them by plus. If you have a division problem, then you can subtract them. So the ln of m times n is the same thing as ln m plus ln n. If it's division, it's subtraction. So, but look at this equation. If I take the ln of this entire equation, which means I take the ln of both sides, which I think the ln of y equals the ln of x squared plus 1, x plus 3 to the power 1/2, x minus 1. So far, so good? Because what this means I can do, on the left-hand side, I have ln y, but on the right-hand side, since we have a product on top, I can distribute this ln to all these terms. So I have the ln of x squared plus 1 times x plus 3 to the power 1/2 minus the ln of the denominator. Whatever's on the bottom has a negative in front of it. Now I have a product here. I can distribute both of those. So I have ln of x squared plus 1 plus ln x plus 3 to the power 1/2 minus ln x minus 1. We haven't done anything difficult yet. We're just rewriting it. The reason this is much easier than using the product and quotient rule, because now we just take the derivative of the ln's. What is the derivative of ln y? One over y. What else? Remember, whenever you take a derivative of y, what do you have to put after it? dy dx. Because it's implicit differentiation. Whenever you take a derivative of y, you take a derivative like normal, but then you have to take dy dx because you're taking the derivative with respect to x. Now this one. What's the derivative of this one? Remember, the derivative of ln u is 1 over u du dx. So the derivative of this one is 1 over x squared plus 1 times the derivative of this, which is 2x. Plus, whoops, we have an exponent. Exponents go out in front. So we finished the first one already. It's going to be 2x over x squared plus 1. 1/2. The derivative of this equation is 1 over x plus 3 times the derivative of 1 plus x plus 3 is 1. Minus the derivative of ln is 1 over x minus 1 times the derivative of x minus 1, which is 1. See some blank stares. Whatever's inside the ln part, that goes on the bottom. And then on top goes the derivative of it. So the derivative of x plus 3 is simply 1. Because 3 is a constant, disappears. Derivative of x is 1. So right now we have 1 over y dy dx two x over x squared plus 1 plus 1 over 2x plus 3 minus 1 over x minus 1. Are we done? No, because we have to solve for dy dx. What do we have to get rid of? We have to get rid of this. How do we get rid of the 1 over y? Multiply both sides by y. The rest of that equation inside parentheses or bracket. Are we done? No, why not? Well, we have to, what is, okay, these cancel. So we have dy dx. But what is y? Y was the original question, right? Y was the original question, which is this whole thing. So we put that in place of y. Which is x squared plus 1, x plus 3 power 1/2 over x minus 1 times our whole bracket here. And we're as good as done. Now, what does this whole equation just find for us? What does this whole equation mean? What does it all equal? It equals dy dx. What is dy dx? Well, what does it mean? What is dy d over x? This is the formula for the slope of this equation at any value x you give me. So if I said, what is the slope of my function when x is 3? I'd plug in 3 inside there and see what I get. That would be my rate of change at that point. Remember, I'm not trying to trick y'all. It's just everything relates back to what we did in the first week of school. So far, everything we've done in the first 7 weeks of school is figure out different ways of using and interpreting the slope of a function. Okay. Now we're going to look at irrational exponents and the power rule. This is the general version. What does irrational mean? Yes, but a little bit more specific than that. By definition in mathematics, if a function is not rational, it's irrational. So all it says is an irrational function is a function that's not rational. So what is a rational function? A function that has terminating decimals. For example, 3, because that's the same thing as 3.0, 3.25, 2.71415. It ends. Or has repeating decimals. Point 33333. Yeah, it's boring writing all those threes. In mathematics, we have a shortcut. See all these dots at the end? That means it goes on forever. What we use in mathematics is if a number is repeating or a pattern is repeating, we put a bar over it. That means that number is always repeating. One point two five two five two five two five. So what I put here is 1.25. Since this pattern repeats, I do that. So a rational number is any number that has either terminating decimals or repeating decimals. We can predict what's going to happen. An irrational I should put irrational number. Any number that is not rational. Yeah, it's just any rational number, any number that's not rational is irrational. That's by definition how you see it in math books. Recap. If I give you this, we can rewrite that using exponentials. We just did that a second ago. It's e to the power n ln x. There's actually, let's start with this. X to the power n is the same thing, e to the power ln x to the power n. Because the e and the ln cancel, it's x to the power n. But since you can't have exponents, we can rewrite this as e to the power n ln x. So we can rewrite those like that. What is the general power rule? You remember that? It's the derivative of any power, any function x raised to the power n is equal to n x to the power n minus 1. That's the general power rule. How do we prove that? We've never proved it. How do you think we'd prove that? Let's see. So we're going to take the derivative of x to the power n. Yeah, we know that the shortcut, move the power n and subtract 1. But why? We know that this is the same as that. If we take the derivative of this side, what do we get? What's the derivative of e to the u? du times du dx. So we start off with this equation here, which is e to the power n ln x du dx, which is the derivative of the exponent. That's du dx. So we have e to the power n ln x. What's the derivative of n ln x? The derivative of n ln x with respect to x. We're only taking derivative of stuff with respect to x, so the n goes out in front. What's the derivative of ln x? One over x. So that equals n over x. So the derivative of n ln x is simply n over x. Well, we haven't gotten to the proof yet. Look at this. We can rewrite that as ln x to the power n, because the coefficient now can go back up to being a power. The e and the ln cancel, so that just leaves me x to the power n. In this part, we have x to the power n divided by x. What's that? What's another way we can write that? What that really means, what's the exponent on the bottom? What's the exponent of this one? And the rule is, if you're dividing the same bases, what do you do with the exponents? Subtract, so that's n minus 1. So these two become x to the power n minus 1 times n. There's the proof of the power rule. Look for an example here. All right. Differentiate this function. Given this, x to the power x, where x is greater than 0, find the first derivative. So how do we do this? With what we just discussed a minute ago, how do we go about this? We know f of x equals x to the power x. What's another way of writing that? E to the power what? Right. That's the same thing. And that can be written as e to the power x ln x. So the derivative of x to the power x is the same as the derivative of e x ln x. So the derivative of this side is equal to what? The derivative of EU is EU du. So it's leave it alone times the derivative of this product right there. So this is f and g. The derivative of f is 1. The derivative of g is 1 over x. We use the product rule. Ln x times 1 is ln x plus x times 1 over x, which becomes just 1. And there we have it.
So what is not auto-sampled, so was the previous one, the one with n ln x to n number of, but this one is n ln x to ln x plus 4x times the 1 over x.
Okay, go again one more time. We did the last one.
Yeah.
We had leave the function alone. And well, this one, because that's not a function of x. That's a constant. So all we have to do is take the derivative of ln x, which is 1 over x. There's a difference between n ln x and x ln x. This is a product rule. This is like 3 times ln x. The 3 doesn't do anything to the function. But that because we have to take a derivative with respect to x. That's a product rule. Good, very good observation. Okay. Oh, one last thing. It's a concept, a theorem, and then we're finished with this section. The number e as a limit. What is the number e? It's a constant. It's an irrational constant, 2.7181715. It goes on forever. It's used to define the e function, which is used to define the ln function. So now, how do we define the e as a limit? So e, remember, as x approaches 0, this is the formula that is defined as e. Because if you take the derivative of this side, then you get the function of e. Okay, that's it for that section. Now we're going to finish up the chapter, I hope, if we have time. This is in section